Hello everyone. Today we're going to talk about how do we describe a certain data set. Now there are certain numbers we use to describe how a data set looks like. Some of them we know or we may have heard of, others we may not have heard of, but we'll go over all of them just to give an idea what they are, and we are going to see how to implement them in Excel. So some of the descriptive statistics, or the numbers we use to describe data, are the mean, or what we call the average, median, the mode, variance, standard deviation. These tell us about the spread of the data. Same thing with range. Quartiles tell us how the data is arranged. Coefficient of variation also tells us about the spread of the data. We're also going to talk about different types of outliers that we may have, and we are going to use z-values to understand those outliers. And then finally, we will talk about covariance and correlation. So let's look at data. I have downloaded this data from the Census Bureau. It is basically from a survey called the American Community Survey, and it has the numbers are the per capita income in the past 12 months. The way it is calculated is it's looking at total income earned in a state divided by the total population in a state. So this gives us an idea of how rich or poor a state is. So we have data on the 50 states in the United States and the District of Columbia. And right now the numbers are arranged alphabetically or by state. Now, if I were to find the average of this number, so if I were to look at the average value, the average formula that we know is basically, if I were to write down what is the formula for that, so this is my formula for the average. I am summing all the values, so each of the entries is denoted by xi. So if I have 50 states, my n will be 50. I have a total number of 50 entries. Actually, with District of Columbia, I have 51 entries. So the subscript is telling us this is the value of the x1 would be the value of the first state that we have in the data. X2 would be the value of the second state. So we are adding all those from 1 till 51. And then first we add all those values, then we divide it by the total number of entries we have, which is 51. So if we go back to our data, we now have, what I can do is I can add all this number, which is sum of all the way up to Alabama, and I get an error message. And the reason is, well, Excel thinks that these are not numbers. If you see a small green arrow in the corner, so what I need to do is I need to convert them to numbers. So I click on that, and now my numbers are converted to, or the numbers that were converted as text are now converted to number. So once I do that, I have a total value of sum divided by 51, and I would get the average, which is 37,099. Another way of finding it is using a pre-canned program that we have in Excel. So we can also calculate the average value is equals to the average, and then I highlight all these numbers and I click enter, and I get this number. Now one question may be that why are there no decimals afterwards? So we can add the decimals. If I go up here right under numbers, if I click on this one, I get 2 decimal places, same as this average value. So we can find the average value in both ways. Well, this is an easier way of doing it. Now the other numbers that we are interested in is the median. The median basically tells us the middle value. So in other words, since it's the middle value, it will tell us that half the data is below the median and half the data is above the median. And the formula that we use in regular case is basically, if I were to calculate median by hand, I was going to just write this, something like this. So if I insert my equation here, median equals to 1 over 2, and then times n, or n plus 1, where n is my number of observations. So if I have, in our case, if I have, let's say, 51 states that I have, including DC, 50 states and DC, then this number will be 52. So my median is going to be the 26th number in the table. So if I go down here, now the one thing is, before we find the median, since it's a middle value, we have to actually arrange this number in ascending order or descending order, whichever one you find is easier. So let's do that. Let us highlight all this number, and we will go to Data, and then click on Sort. Once I click on Sort, right now, I have clicked my data has headers. That's why it's not including this. Now I want to sort it by per capita income from smallest to largest. So once I do that, the reason I highlighted both of them is that once the numbers changed, the order of the states also changed accordingly. So now I can go to the 26th value, and I can keep on going to, so this is going to be the 26th value. So the median is then 35,189. Another way of doing it is just going to Excel and saying median, and then highlighting all the numbers. And we should get 35,189, which was, so then we would say that the median value is this number, and it is telling us that half the states have a per capita income of lower than 35,189, and half the states have it above 35,189. I'll consider DC as a state here too, so that I don't have to say states and DC. It's just easier just to say all the states here. Other value we are interested is mode. Now mode is telling us which value appears the most times. Now in our case, in this case, we probably will not have a mode because chances are two states having the exact same number is probably going to be very close to 0. But it's worth a try. Let's see. And it will give me a error message saying there isn't one. Let's look at another data. Let's say we have a data like now. If I were to find the mode here, I would basically highlight all this number, and it would give me the number 7 is the mode because it appears the most number of times. So the number that appears with the highest frequency is the mode. And in our case, since all the numbers appear just once, so there is no mode. Now from here, we can also find what's the maximum value and minimum value. So if I go and add maximum and minimum, I can write equals to max, and it will give me, and if I highlight all these numbers, and it's telling me that the maximum value is 63,793, and that's the per capita income of Washington, D.C. The minimum would be, if I just do equals to min, and just highlighting all those numbers, it's telling me the minimum value is 26,807, and this is the value of Mississippi. So I will just write the names of, or how I calculated these values right next to the numbers, or the generated numbers. And so from here we can look at what is the range. The range is going to be just the difference between the maximum and the minimum, which is telling me how much is the data distributed. So the range is 36,000, around 36,000, or close to $37,000. So we have looked at the mean, median, mode, the range, and now let's look at the variance and standard deviation. The average value, it's telling us, it's just giving us a number, and the average, the way we think about average is if I were to use one number to describe the data set, what would the number be? And so it is the average. However, the average has some issues. Although we do rely a lot on averages, but average without the range or the variance of the data kind of gives us a wrong information. Let's say that we have two data sets with three numbers. So the first data set has three numbers in it, and each of the values is 10. The second data set is 10, 15, and 5. So if I were to find the average of these two numbers, or these two data, the first one will have an average of 10. The second one also have an average of 10. But I can see that in this number, or in this data set, all the numbers are the same number. So there is no variation in the data. So I can say that in this case, variation is 0 for this data because all the data are of the same value. On the other hand, this one has some positive value. So this is telling us that there is more variation within the data. And then if I present both these averages are the same, without knowing the variation, I will make some incorrect assumption about how the data set is arranged. So the next thing we can talk about is the variance of the data. So variance is basically, look, if I were to describe what variance is, it is just the spread of the data. So let me write it up here so that it would be easier to follow. Variance, it's just how much the data is spread. So if I were to find what is the variance of the data, the formula is going to be basically this value. So variance equals 1 divided by. So this is the formula of variance. What it's doing is that it's taking each of the values that I have, subtracting that from the mean, and then squaring that value, adding it all up, and then dividing it by the number of observations minus 1. So let us look at step by step. So first, we know what the average is. So the average value I have is 37,099.37 or 37,099.37. What I will do is I will write equals to the number minus 37,099.37. So I'm subtracting each value, and I'll do that for all the values for every state here. So this is my number, and this is the formula. So what I can do is I can toggle this cursor over here, and if you come across here, you will see that a black cross is formed at the corner. I will hold my mouse down, and then I'll drag this all the way down. And what Excel does is it copies all the formula. And if you notice, it is copied all the way down here. So after I do that, this over here, the next is I need to square that data. So what I can do is I'll take this data and square it, and I get a huge number. So, and if I drag my mouse again all the way down, I get this number. Then my variance would be, basically it will be the sum of all these numbers, okay, divided by, I have 51 entries minus 1. Why do we subtract 1? It's because of degrees of freedom, and we'll talk about that in a later lecture. So I'll just leave it for now. Just think that it is divided by 1. I made a mistake here, so let me first fix that. I need to put a parenthesis before 51. And I get this huge number. Now, as you can see, this is a really big number, and it can be kind of daunting to understand. Like, the number is 41 million, or a little over 41 million. Now, instead of doing all these steps, what I can do is just calculate the variance in a much simpler formula. Variance will be equal to, I'll write var dot. Now I get two vars, variance.p or s. P is if I have the whole population. S is if I have just a sample of the population. So we're just going to use S for now, and then we will talk about the others. And then var.s, and I will select all these numbers, close the parenthesis, and I should get the same value. Now, this will be my variance. So I also get 41,033,058. So this is a huge number, and it's hard to comprehend what it is. So we look at something called standard deviation, which is basically the square root of the variance. Let me write the formula of variance in this corner. Copy and paste it so we can see what it is. And standard deviation will be the square root of the variance. The standard deviation is just talking about the variance, but showing it in a much smaller value. So one thing we know with the variance number, if the variance or standard deviation is a higher number, then the data is more spread out. That means the spread or the width of the data is much more if this number is higher. So if I have two data set and one data has let's say there are two data set, S1 is the standard deviation of one number and it is 50. S2 is that of another number and it is 80. Then I will say that the second data has a higher variance, which means the numbers are more spread out in the second data set. So in our case, my standard deviation is 6,405. So if I were to, this value is of 2021. Now let's say in a couple of years I do the same exercise. Let's say in 2023, if I were to find the standard deviation of these numbers, and if the standard deviation is a lower number, then that would mean the numbers are getting closer to the mean. So in other words, let me just write it again here. The other number we are interested in is coefficient of variation, or we call it CV. Coefficient of the variation, or CV, is basically the standard deviation divided by the mean. Our standard deviation is 6,405.70, and our mean that we calculated is, so the coefficient of variation would be just standard deviation divided by the mean. So which is 0.1727. This number actually helps us to understand, like, let's say if the mean were different, but the standard deviation were the same of two data sets, then which data relatively had a bigger spread of data. So it's telling us, let's say, if I'm looking at two different data sets, say the standard deviation is the same, but the mean is different for each of them, then which one would be, if I found this number, and the lower the number, the closer, or the relatively, the standard deviation or the spread of the number is less when the coefficient of variation is lower. Finally, we use another type of data, which is called the quartiles. We used one type of quartile already, which is the median, but quartile comes from the word quarter, which means 1/4. So first quartile is basically the first fourth, then the second quartile is the median, and then we come with the third quartile. So quartile is telling us what is the position of the number. So if we looked at the value of the median, which was 1 over like n minus n plus 1. Let's change this back, which was n plus 1. So in our case, the first quartile it's just going to be 1/4, 1 over 4, n plus 1. And the third quartile will be 3/4 times n plus 1. So this tells us how the numbers are spread out. And let's go back to our data. So the first quartile is going to be equals to total number of variables we have, which is 51 plus 1 divided by 4. So the number is 13. So what I would do is go to the number and go to the 13th data, which is 33378, that of Utah. So the number is 33378. I'll put this number, I'll delete it for now because the number we're interested in is actually this number, not the 13 value. So let me remove some of the decimals because there's quite a bit of decimals around. The median, as we found out, was equals to 51 plus 1 divided by 2, which was the 26th value, which we go down to the 26th value, which is actually this number, which was 35189. And then finally, the third quartile is going to be equals to 3 over 4 times 51 plus 1, which comes out to be 39. So I will go down to the 39th value, which is Rhode Island's value, which is 39603. Now this is telling us how the numbers are arranged. So the first quartile is 33,378. So this is telling us that if I were to visualize the data without looking at the whole data, here we have 51 lines of data, so it's easier to visualize it. But what if I had like thousands or hundreds of thousands of lines of data? Then these numbers give me an idea how the data is spread. So I know that if 1/4 of the data is below 33,000 and 1/4 of the data is above 39,000, then half the data is between these two numbers. So between about 6,000 values. Now, one thing I can actually do with this number is that economists and statisticians and many other social scientists use is what we call a box plot. What a box plot is, what I will draw is looking at how the numbers are shaped. So I need these three numbers and I need the max and min. So the max and min are these two numbers and so the box plot is telling us if I were to draw it, so I would draw a straight line first. Hopefully that is a straight line. And then I will say that the minimum value is going to be 26,807. And the maximum value that I have is 63,793. Now from here, I know that 1/4 of the data has a value of 33. So, and this one, and I will draw a box here to 39. And this will be the median. So the median is 35189. And the first quartile is 33378. And the third quartile is 39603. Now, if you notice, actually our number here is going to be a lot longer. So let us make this line a lot longer. And now we will say the max is 63,793. So this is telling us then what the data looks like. I know that the data ranges from this to this. This is the minimum value. This is the maximum value, okay? So the first 25% of the data is here, and then the next 25% of the data is here. So visually, I can also see that the later part is much more spread out than the earlier part, and I can see the range here between these two numbers. It's about 8,000 or a little less than 8,000. Here, it's much higher, between 39, 49, 59, almost like $25,000 range here. And this is telling me that part away. So 50% of my data is in this range. And this is the first quartile. That's the third quartile. And this is the median. So this box plot, which is the black part, this is telling me then how the data is distributed. And it's a very nice, easy way to see the spread of the data. So afterwards, once we found out all those numbers, other number we are interested in is the interquartile range, which is just the difference between the third quartile and the first quartile. So third quartile minus the first quartile. So we go 39,000 minus 33,000, which comes about to be 6,225. And that is my range of my data. So the middle 50% of the data is has a range of 6,225. Okay. Now we have talked about, now let's look at outliers. Outliers are usually data that are considered to be far away from the mean. And how far away is kind of relative to understand, but what we do is we first to understand outliers, we calculate what we call z-values. A z-value, the formula of a z-value is just going to be, and later in other videos we are going to use a lot more z-values, but for now we are going to use z-values to understand outliers. So z-value is basically just xi minus the mean value. So from here we know that x bar is the average of the sample and s here is the standard deviation of the sample. So what we need is all those numbers, so we can just write those numbers here. We have the numbers here actually, so I'll just copy this number here. So what I would do is equal to the number minus the mean, which I can select this way, divided by the standard deviation. And so I get a z-value of -2. Now I can pull this down here, but one thing that happens is that the numbers get off. What Excel does is that as I move it down, it also, if I click on this one, number 1, it also moves these numbers down. So the next one is down here, or let's click on down here. So it's thinking that there are numbers here. Now that's a problem. So what I can tell Excel to do is I can go to my formula and I can put dollar value before the letter and the number for the numbers which I want to be held constant or still. So that I'm telling Excel that, hey, don't move these numbers as I copy the formula below. So once I do that, now if I redo it, I can see that if I click on the number, it stays at those two values. So I will keep on doing that. I will go all the way down to this number. And what we see is, well, the numbers are actually in whole numbers. We can convert them to decimals just to make them a little. If a z-value is greater than 3 or less than -3, we call that number an outlier. So this tells us that if I were to find data that were way out of the number zone, so then I would see that what number is going to be an outlier. And so this is one easy way of finding it. And so if I look at the top numbers, well, none of these are outliers. They're within that range. The only one that seems to be an outlier is DC, which is at 63,790. So our outlier here is per capita income. And so that number helps us to see if there are some numbers that are way too high or way too different from the rest of the numbers that we have. Now, we have been talking about averages of, mainly we talked about X bar and S of what we called a sample. Now in statistics, we make a distinction between the sample and a population. So if I were to look into what exactly are these things, so a population is basically all the data points available. So if I were to look at all the, let's say that I wanted to calculate what is the average value or average income in America. So then the US has 330 million people living within its borders, a little more than that. I could survey all the 330 million people, find their incomes, then add all the incomes and divide it by the total population. And that would give me the population mean. And then I can also find the population variance and population standard deviation. So when I talk about the population mean, I use Greek letters to denote them. So the Greek letters for population, it's going to be the letter mu, just right here. And the Greek letter on the value for, let me first write that here. So mean is denoted by mu and standard deviation is denoted by the letter small sigma. So, and the way we talk about variance, if I were to include variance, it is basically sigma squared. So I would write it as that. Now this is of the population, but usually, as you can see, surveying 330 million people is very difficult. So the numbers we have been using here, it's basically from a sample. So a sample is just a subset of the population. So a sample is a subset of the population. Now in later lectures, we're going to talk about how to get the sample to mimic the population. And we do random sampling for that. But a sample, it's, as we said, it's very difficult to survey every single person in the United States. Maybe it's just some people are not willing to respond to a survey, or maybe their survey gets lost in the mail, or they get lost in other ways, or just it's not possible to calculate all of that. So maybe what we do is, instead of surveying all 330 million people, we can survey 30,000 people. And so this 30,000 people would be my sample size, and we would call this the sample size. And then from here, we can also calculate the mean and standard deviation, and also the variance. But these are going to be the sample mean and sample standard deviation and the sample variance. And the sample mean is what we used in the other part. We called it X bar, so I'm just going to copy this. Standard deviation would be S. Some people put S bar. We don't need to. S is fine. And variance is S squared. So whenever we're talking about sample, if I say the sample average, I'll use X bar to denote that. If I talk about this as the population average, I'll say mu equals that. And it is an important distinction to make because the population this is the data we would love to have, but we may not be able to get this all the time. So what we do is we get the sample, we get these values, and then we try to figure out and see if these numbers are close to the population numbers. So with that, the other thing that it does help us to understand with these numbers is the final two things we're going to look into is covariation and correlation. Covariation and correlation is basically just how two columns of numbers are related to each other. So what I will do is I will sort this again, just because I have another type of correlation numbers or another set of columns of number in another spreadsheet. So I'm just going to match it with that. So covariance and correlation tell us about how two sets of numbers are related. So I also have this number these data of percentage of individuals in a county or in a state that have more than a bachelor's degree or higher. And I have a per capita income. So this number, again, these numbers are not stored as numbers, they're stored as text. So what I need to do is I need to go and click on this and tell Excel to convert it to numbers. So it's telling me that Alabama has 27% of people with a bachelor's degree or higher, and this is where I get the data set from. Now, covariance is just telling us how two of these values are related to each other. So the formula for that is just covariance of, again, since we are using sample, we'll say .s. And then it's telling us what's the first array of data, and I'll say it doesn't matter which one I put first, but it is telling us this, comma, then I'll say what is the second array of data, which is all this, and then I click enter. So that's the value for covariance. So covariance really doesn't tell us much other than, I can't say that if covariance is higher, that means the numbers are more related to each other. What I can say is if covariance is greater than 0, then if one value goes up, the other data's value also goes up, which means that if per capita income goes up, education attainment goes up, or if education attainment goes up, per capita income goes up. That's all it tells. If covariance is less than 0, then if one value goes up, the other goes down. So they're negatively related. And if covariance equals 0, then there is no relationship between these two numbers. So this is covariance. The other number we use is correlation, which we will just say equals to correl. And again, we select those two columns of numbers, and it gives us a number. Because covariance, the number, does not really tell us anything about whether a number is more correlated or less correlated, we use correlation number. So correlation ranges from -1 to 1. So 1 means perfect correlation. So if, let's say, 1 bachelor's degree or higher, if this column goes up by 1 unit, per capita income goes exactly by 1 unit. So they are correlated at the level of 1. If correlation is -1, that means they go in opposite direction. If one goes up by 1 unit, the other one goes down by 1 unit. And a correlation of 0 means they don't. There is no relationship. Now, correlation does not mean causation here, which means that correlation just tells us that these numbers move together. It doesn't tell us if one causes the other. So we need other methods, and that's where economics comes in. We need other ways to figure out if one number makes the other number move. So that's where we need economic theory and economic understanding to figure out is it educational attainment that is causing per capita income to go up, or is it increasing per capita income that is causing education to go up? But correlation itself does not tell us that there is causation. Well, hopefully this lecture was helpful. I will see you at a later lecture. Have a good day.